So today we'll be going over the rules of differentiation. So first we'll be looking at the constant rule, which basically says that a derivative of a constant number of a constant is equal to 0. So let's say I had the function f of x is equal to 7. 7 is a constant number. So the derivative of f of x at 7 is going to equal 0. That's basically what the constant rule says. And also, before we start the rest of the lesson, I have to define what a derivative says. A derivative basically just tells you the slope of the secant line. So, next, we're going to look at something called the power rule. Power rule. So, if you have a function, for example, where f of x is equal to x to the n, where n is a rational number, we can assume that the function is differentiable. And to find the derivative of this number, what the power rule states is that you can write this as f of x, f prime of x, of n x to the n minus 1. So let's test this theory out. So f of x is equal to x squared. The power rule tells us that the f prime of x will equal n to the x n minus 1. In this example, n is equal to 2, x is x, and n minus 1, 2 minus 1. So that will give us an f prime of x of 2 to the x. Right? So we're going to prove this. We're going to prove this derivative right here using the definition of a derivative. The definition of a derivative states that the limit as the change of x approaches 0 is f of x plus the change of x minus f of x all over the change of x. So our function, remember, is f of x equals x squared. So what we're going to be doing here is the limit as change of x approaches 0 of f of x plus change of x. So we're going to write this as x plus change of x squared minus x squared all over the change of x. Now we're going to simplify this equation. So the limit as the change of x approaches 0, x squared plus 2x change in x plus the change in x squared minus x squared all over the change of x. So we see here that the two x squares will cancel out, right? So we're left with the limit as the change of x approaches 0 of 2x plus the change of x plus the change of x squared all over the change of x. So now we're going to factor this equation. The limit as the change of x approaches 0 is going to be the change of x 2x. Oh, I'm sorry. This plus sign shouldn't be here. My mistake. We're all math people. We make mistakes. It happens. Okay, so 2x plus the change of x all over the change of x. Oh, look. These change of x's cancel out. Now our denominator isn't 0 anymore. So now we can work with this function. The limit as change of x approaches 0 is equal to 2x plus the change of x. Now we're going to substitute the change of x for 0. We're actually going to do the limit now. So the answer comes out to be 2x. Whoa, look! It matches. Why? Because the power rule works. now, if you still don't believe me, you can do this again with another function. Let's say our function is the f of x is equal to 5x squared plus 1. So now we're going to follow our power rule. So f prime of x is going to equal, remember, nx to the n minus 1. Right? This is plus 1. So the f prime of x, in this instance, again, we already have an n. Our constant is 5. That's going to be in front of the x. So 2 is our n. So 2 times 5 times x. 2 minus 1, which is going to equal 1, plus. And then now we're going to apply our constant rule. Remember our constant rule before stated that the derivative of any constant number is equal to 0. Sorry, this should be a 7. Yeah. So we're going to apply it back here. So now we know, based on the constant rule, that this 1 will be a 0. So our derivative comes out to be 10x. Now we're going to prove this again to show that the last time wasn't just a fluke. So the definition of derivative is a limit as the change of x approaches 0 of f of x plus the change of x minus f of x all over the change of x. Right? So the limit as the change of x approaches 0, our function here is f of x squared plus 1. So we're going to plug an x plus change of x into the x squared, right? So 5x plus the change of x squared plus 1 minus f of x squared plus 1 all over the change of x, right? So now we're going to simplify this a little bit. Make sure to always write the step. It's very important. If you leave this off, you'll get points off. So 5 times x squared plus 2x change in x plus the change in x squared, or delta x, whatever floats your boat, plus 1 minus 5x squared minus 1 all over the change of x. Okay, so now we're gonna distribute this 5 so we can better understand this problem. So 5x squared plus 10x change of x plus 5 change of x squared plus 1 minus 5x squared minus 1 all over delta x. Now, we can immediately see that these two 5x squares will cancel out. This 1 and negative 1 will cancel out. And now, we will be left with the limit as delta x approaches 0 of 10x delta x plus 5 delta x squared all over the delta x. Now, our problem here still persists with the delta x in the denominator. So we have to solve for that. What we're going to do is we're going to factor the delta x out. I'm only writing on the side because I'm running out of space, but you should do all your steps like in a series going down, not sideways, because that keeps your work organized and concise. Okay, so we're going to factor the delta x over here. Delta x, 10x plus 5 delta x all over delta x. Now look. So we're left with the limit as delta x approaches 0 of 10x plus 5 delta x. Now we're going to solve for the limit. Now we can plug in the 0 for the change of for the delta x. So we're left with 10x. And unsurprisingly, it matches because the power rule works every single time. So this saves you a lot of time and effort, and the steps will take, like this took me like 10 steps at least to get the derivative, and much longer than it took me to do the power rule. Okay. Now, there's also special derivative rules involving the trigonometric functions. For example, the function sine of x has a derivative at cosine of x. And the function of cosine x, the function is cosine of x, the derivative, you would expect it to be sine of x, right? Because the derivative of sine of x is cosine of x. However, the derivative of cosine of x is negative sine of x. So one important thing to remember here is that just because a number is derivative of a number doesn't mean that the reciprocal way works as well, as shown in this example. And there's a couple of other ones. The function of tangent x, the derivative at this number is going to be secant squared x. And the function secant of x, the derivative of secant of x is going to be secant x tangent x. And the function of cotangent x, the derivative of cotangent of x is going to be negative cosecant squared x. The function of cosecant x, the derivative at this point, at this function, is going to be negative cosecant x cotangent x. So these you basically have to memorize. They're going to help you in your later functions and problems that will come up later. And one easy trick to remember these is that the tangent of x can be is this trick right here. I'm going to show you. Secant, secant, tangent. Function tangent x. What is the derivative? The secant squared x. Similarly, the secant of x, what is the derivative of secant of x? Secant x tangent x. This rule also applies, this trick will also work for cotangents and cosecants. However, there's a negative sign. Negative cosecant, cosecant, cotangent. So whatever function you're looking at, just ignore it in the sequence and look what the 2 multiply will get you. So the cotangent of x, the derivative of that, will be negative cosecant squared x. And cosecant x, the derivative of cosecant x, will be negative cosecant cotangent. Right?